do very basic things about geometry, geometric structures in general, so that you could get prepared for more advanced lectures. So, what is the geometric structure? So M being a GX manifold, this is a GX manifold. This means there is an atlas so UI is some open set in the manifold, and phi sub I, this is some homeomorphism or diffeomorphism from this UI into this model manifold X. Okay? And it satisfies this transition law. Suppose you have a manifold here. So you have two overlapping atlas. Then this is mapped to some open set in X. This is mapped to another open set. So here is an image of this overlapped part. Then you can think of this transition map. So this will be a phi I inverse phi j. Okay? So if you just restrict this transition function from the image of this overlapped part, this is a restriction. This is a restriction of so phi j composition phi I inverse. So restricted to this is a restriction of some element in G. Okay, so you restrict this thing. Okay, so G is some group or groupoid, and you have a model manifold X. And you can cover the manifold by the union of these open sets. And each open set has a copy. Okay, its copy in model manifold, and transition functions are required to belong to an element in G. So for example, if you take G as some local homeomorphisms in Euclidean space, then it's just a topological manifold. And if you take G as some groupoid of local diffeomorphisms in Rn, then this guy becomes a differentiable manifold. Okay? Is it clear? Graduate students? So this is a general geometric structures definition. So I'll give you some examples. So as I mentioned already, if G is a groupoid of local diffeomorphisms, on Rn, so Rn is our model manifold in this case. Then this is just M is M being a C infinite manifold. Okay. Now take more serious one. If you take G to be a Lie group, take a PSL12. And if you take X to be a set of elements in R2, the second coordinate is positive, and the metric is given by, metric here is given by some, it's proportional to Euclidean metric, but as you goes higher and higher, you divide by the height of this coordinate, so that if you have a, so this is an upper half space in R2. The segment here, up here, is much smaller. In Euclidean sense, this one and this one is, they have the same length, but in hyperbolic metric, this one is much smaller. Okay, so the metric blows up as it goes down toward this axis, x-axis, and when it goes up, then this is very exponentially fastly shrinking. Okay, so usually people denote this set X as a two-dimensional hyperbolic plane. And it is well known that in complex analysis that you learn in an undergraduate course, I believe. This is biholomorphic to a unit disk in complex numbers. So this is just a number, complex number, let us say complex number whose norm is less than 1. Okay, so this is biholomorphic. So I start from really basic things. I'm assuming that the people attending here, I mean the graduate students, do not know about any hyperbolic geometry or geometric structures. So even though you are a little bit bored, please be patient a little bit. So I'll describe how does the geodesics look like in this hyperbolic plane. So geodesics, either this is an arc perpendicular to this x-axis, or the other geodesics is like this. Okay, this is a half line orthogonal to this x-axis and shooting up. Okay, these are the only types of geodesics in hyperbolic plane and in general hyperbolic space. And what is this G? G is more than just a group. In this case, this is a Lie group. Okay, and among Lie group, this is also a semi-simple Lie group. And furthermore, this is a rank 1 semi-simple Lie group. So if you study this GX manifold, where G is PSL to R and X is this is a hyperbolic 2 plane, you are studying hyperbolic geometry in dimension 2. Okay, so it is known that every surface of Euler number negative admit some complete hyperbolic metric. Okay, so maybe I'll just say G is, this is a group of orientation preserving isometries. Okay, so this is a group of orientation preserving isometries. So if you allow orientation reversing isometries, you can reflect this thing, for example, along this perpendicular geodesics. And that's again an isometry, but the orientation is reversing. And what else? Also, this H to R is homogeneous space under the action of this G. Okay, so this group G acts transitively on this plane, so it's a homogeneous space. And the stabilizer, for example, here is I. So stabilizer of this point in this group, you can easily compute it. That is exactly SO2. Okay? So this is an isotropy group of the one point. So this H to R can be written as a G mod, the G quotient of some compact group. Okay? So as I told you, by the uniformization theorem of alphas, any topological surface with negative Euler characteristic number can be written out H2 mod gamma. And gamma is a discrete, torsion-free. This is discrete, torsion-free. A subgroup. Okay. So if you can find some, in this case it's called the lattice. If you have some discrete a group acting properly discontinuously on this model space, you can quotient out this model space to obtain some geometric manifold. And if you allow some torsion element here, it is a cone manifold. So I think you will hear more about this cone manifold and obifold later. Okay, so well, just for fun, let's draw some pictures. Choose some generator of the fundamental group. So I wrote alpha, beta, gamma, and delta. Well, this is actually this is sort of a homotopy class, free homotopy class of that generators. Then you can a little bit visualize this action like this. So this is a unit disk in complex numbers, and you have how many? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So you can glue this this octagon to obtain this genus 2 surface. Then alpha here represents some hyperbolic isometry acting like this. For example, like this. Okay, this is an alpha. So it's a translation along this geodesics, and you glue this side to this one. Beta being like this. Okay, and gamma and delta. Gamma and delta. So out of these 4 generators, which are hyperbolic isometries, you can generate this gamma. So if this is the case, because there's a fundamental domain by Poincaré theorem, this gamma is a discrete subgroup. And obviously, if you quotient out this H2 by this action, you have a finite volume here. So it is a lattice. Okay? So, okay, our acting president, he arrived very late. Maybe you can give later. No, you have. No. I will finish after like 1 hour or something.
That's okay.
No, it's too much. Just go ahead. It's just a few minutes, and then you could be free.
Hello, my name is Kim. I came very late this morning. Sorry, I came from Suwon, and it was a 55-kilometer trip. Actually, I'm very glad to have you here. Professor Inkang Kim was the first research fellow in KIAS. And at that time, we had just 1996. It's 14 years ago, in 1996. It started with just 4 members. One professor, Professor Hyo-chol Myung at that time. He was the acting president. And regretfully, he passed away about a month ago, February 11th. And he did a great job to establish and to found this great institution. And Professor Inkang Kim was the #1 research fellow. And he went to Seoul National University, then he came back. And so right now, so it started with just 4 members. Now we have 130 members, professors and research fellows and the staff members. And also we have, every year, we have many foreign visitors and also domestic visitors, professors. And so it's a kind of a booming institution. And, but we are dealing with only mathematics and theoretical physics. And also, I belong to computational sciences, School of Computational Sciences. And what I'm doing is the quantum computer and quantum algorithms and also quantum cryptography. And these are all related to what you are doing, geometry and algebra and the number theory. So actually, this is a great institution for intellectual exchange. So, and also, I'd like to add a little bit more.
Yeah.
Can I do that?
Yeah, sure.
And if you are a foreigner, while you are here, just enjoy the Korean culture a little bit more. And among them, I'd like to introduce the Korean characters, for phonetic characters. This is a great one. And also, Korean culture is full of symbols. If you visit the palace, then you can see, you do not see just buildings. It's full of the symbols and meanings. And these Korean characters, we have 14 consonants and 10 vowels, and 14 consonants are made of from the shape of sound organs. So if you learn that principle, you can easily learn Korean characters, how to pronounce. And also, Korean vowels are derived from the Oriental philosophy, heaven, earth, and human being. So if you do not know anything, that's just the colors and shapes, but if you start to understand, that's full of symbols and meanings, like what you are doing in mathematics. By the way, I didn't say my name, right? My name is Kim, and I'm acting president, and my office is on the 2nd floor. If you want to meet me anytime, just come to my office. Thank you very much, and great workshop. Thank you.
Okay, thank you. So this is the beginning of the hyperbolic geometry. Okay. I hope I convinced you there's a geometry called hyperbolic geometry, and it seems to be pretty easy. So let's move on to a little bit of generalization of this hyperbolic geometry. So as you can see, this is a round disk in hyperbolic geometry, and it's an ellipsoid actually. So let me talk about a generalization a little bit. So draw any convex domain on R2. Okay? Convex domain on R2. And then I will define a distance, a metric, on this open convex domain. So if you want to measure the distance between this x star and y star, draw a Euclidean a line, then you will have another point x and y which meet at the boundary. So we can do it for any convex domain, but let's restrict ourselves to strictly convex domains. Then the distance between these 2 points is defined as, many people put this 1/2 in front, log of x star y star y. Okay? Take an absolute value to make it positive. So here, what is this x star y? This is a cross ratio defined as a ratio of some product of Euclidean distance. Okay? So you can check, this is a metric space, okay, defined by Hilbert. So this is a Hilbert metric. Okay? So when this convex domain is an ellipsoid, you can do it in Rn, then this becomes a hyperbolic geometry. Okay? So this is a generalization of the hyperbolic geometry that you know about. Then this metric is not Riemannian except hyperbolic case. Okay? So this is usually a Finsler metric. So what is Finsler metric? You can only measure the length. You are not allowed to measure the angles. Okay? So in general, you cannot define the angles. So this is a Finsler metric. So if the model space is some strictly convex domain on Rn, and if you take a group G as an isometry group of this Hilbert metric, then you have real projective structures. Okay? It's called real projective structures. So in this case, M is a real projective manifold. And if M can be written as this is a convex domain omega, and if you can find some discrete subgroup acting properly discontinuously to give this compact manifold, that is not always the case. And if you draw arbitrary strictly convex domain and define the Hilbert metric, I mean, it's very rare to find such a gamma, such a lattice, whose quotient is a compact manifold. So, but if such a gamma exists, so G is just isometry group with respect to this Hilbert metric, then in this case, omega is divisible. Okay. I'm not sure this is in English or French, but I don't know, people write this way, divisible. Okay. So I told you not every convex, strictly convex open domain is divisible. And if it is divisible, one can show that in this case, this boundary of omega is at least C1. In divisible case, this is at least C1. Okay. So if you draw some convex domain which is not C1 boundary, then there's no such a group. Do you have any questions? The graduate students. Silence. Okay, then let me define what is developing map and holonomy of these geometric structures. So I just remind you that structure, projective structure, is a special case of, so this projective structure is a special case of this is a special case of PG L n plus 1 R and RPN. Yeah, it's a compact manifold. If it is compact, okay, divisible, so M is compact. There are projective structures which is not convex also. Okay, so this is a special case because this is pretty much similar to the hyperbolic geometry. Actually, in this case, gamma is a Gromov hyperbolic group. Okay. Actually, that's the if and only if case. If gamma is some sort of a lattice in this strictly convex projective structures, then gamma is always Gromov hyperbolic. So let me define what's the developing map and holonomy things. These are pretty standards, but somebody has to give basic definitions. So I'm the first one, and I'm forced to define all these trivial things. What is the developing map? What is the developing map? So because I'm lazy, it's better to draw pictures. Suppose we have some GX manifold, right? Okay. Then what is the definition? There's an atlas. Okay, there's an atlas. And each atlas has some copy. So say like phi I is mapped to some open set here, okay, in X. And take a universal cover of this thing, of this manifold. This is M and M tilde. So maybe I'll draw some fundamental domains, for example. Then this copy, you have this image here, and so on. So developing map is analytic continuation of this atlas. So once you fix, let's fix the first image. So pick this open set, and you map this guy here. Okay, there's a choice involved, but let's just fix one open image here. And then you develop these things. For example, here, the next guy, the JSON one, this guy will have some image here, right? J, by definition of GX structures. Okay. Then what you do is we know there's a transition map, right? I defined that the transition map must belong to the G, groupoid G. So there is at least one. Then you glue this two open set in X by that things. So how did I denote it? It was something phi inverse pj, or the other way around. I'm not sure, but you can glue them. Okay. Please turn off the cell phone. So, you can glue these two open sets in X, and you just continue it. Okay? You just continue it. There's another image, but by this transition map, you pull this guy to the next one here. So here you can, develop this image on X. And suppose you have a closed loop, gamma. Then in general, if you develop this series of these open sets overlapping each other, in general, what you will get is something like this, right? They don't close up, usually. Okay. So once you made a choice, you choose one open set and the image, then you can uniquely develop this thing. Analytic continuation gives you a developing map. Okay, because I'm lazy, I'm not writing down all the details, but I hope you understood everything. Okay? So this is a developing map by picture. And I gave you hint if you have some non-trivial element in the fundamental group. Usually the developed image is like this. And you can measure the the discrepancy. It goes and comes back. But here, this overlapped image here corresponds to some element here, this element. So I'll denote by like row of gamma. Okay. So for each non-trivial element in the fundamental group, you can associate an element in G. And you can play around to make it sure that this is a homomorphism. This is a homomorphism. I didn't prepare transparencies because I decided to give lectures on board for graduate students. If not, they usually fall asleep and so on. So. So this row is called a monodromy. So if you fix some base point of this group, say X, you can define this is homomorphism. This is usually called holonomy. Okay? Holonomy. If you have any objections, you can do it. I didn't do this rigorously, actually. I just tried to give an idea to graduate students. And what else? What else? For example, if you take a loop gamma, then developed image was something like this. Something like this. And gamma was here, and gamma x here, okay? So x is a point in the universal cover of M, then gamma acts like this, okay? And this is the picture in X, this is the picture in M tilde, okay? Then you can easily verify that developed composition gamma is actually row of gamma and developed. Okay. If you first send this guy X to here, and then you make row of gamma act on it here, that is equal to send X by gamma on universal cover first, and then map it by this developing map. Okay, this is the rule for developing map and holonomy. Okay? Sounds reasonable. Then there's some substructure of this projective structure called the affine structure. So what is the affine structure? So what is the model manifold? Model manifold is just Rn, and the group is affine group of Rn. Okay? So affine group of Rn is just a linear group together with the translation. Okay? And this translation group is a normal group. Why this is the sub-geometric structure of the projective structure? Because it's easy. I told you this is a sub-geometry of Rpn plus 1 PGL n plus 1 R. Why this is true? Say there's a point, there's a vector in Rn, then what's the rule here? You multiply by a matrix and then translate it by X and do it again by another matrix, and translation, this is BA V plus B X plus Y. Okay, this is the composition in affine geometry. You can write this equation in terms of matrix. Okay, matrix in n plus 1 space. In n plus 1 space. So what is the matrix? I think you know the answer already. Yes?
Before you raise this some question in your second example, so whenever you have such real project manifold,
Yes.
you mean that its fundamental group is Gromov group?
What I said is, if M has a strictly convex real projective structure, then the fundamental group is Gromov hyperbolic. Okay. Strictly convex real projective structure, not all the real projective structure. So I assume everybody knows what Gromov hyperbolic group is. If you don't, please ask. If you don't, I'll go on. So what is the corresponding matrix equation here? How do you write this? I think this is, you put B and then Y and 0, 0, 0, 0, and 1. And then you put A, this is n by n matrix, this is a column vector, X here, 0, 0, 0, 1. If you multiply this out, I think you will have BA, B, am I correct? BA, BX, and 0, BX plus Y and 1, right? So this is a linear part, and this is a translation part. So this affine action can be written as a n plus 1 by n plus 1 matrix equation. Okay? So for example, if you see an affine domain like this, you can view this affine domain in projective space like a triangle. Okay. In affine geometry, you have line going to the infinity, but in projective geometry, so all this line corresponds to one point, so you sort of compactify this line. And sometimes it's useful to look at the picture in projective geometry when you study affine geometry. Okay? There is one unsolved problem for graduate student. Complete affine manifold means, by definition, this is by quotient and gamma. Okay. Or maybe I should have mentioned this. If you look at this developing map, the image is not necessarily entire X. Usually the image of this developed one is strictly smaller than the entire space X. So for example, in strictly convex geometry case, the developed image is the strictly open domain, not whole Rn. Well, that's a bad example. Anyway, in this case, for example, the developed image of this affine structure, for example, is not the whole Rn. But complete, affine structure being complete means this is the developed image is the whole Rn geometric model modified out by some a discrete group gamma. Okay? So that's the definition of completeness. So if you look at the holonomy there for each element, rho of gamma in this case consists of a linear part and translation. So this is an element in GL and R. Okay. There is some conjecture. Linear part of rho of pi 1 of m belongs to S, L, and R. Special linear group. And you know the determinant of the matrix in S, L, and R is 1. So it preserves the volume in Euclidean space. So in this case, it is called a parallel volume. Okay. Not all the affine structure has a holonomy whose linear part belongs to S, L, and R. But suppose it does, then there's a conjecture called Marcus conjecture. He claimed that if compact affine manifold has a parallel volume, compact affine manifold has a parallel volume imply is complete. You can write down M as a quotient of whole Rn by some discrete group in affine group. This is a conjecture. As far as I know, this is unsolved. So this is good problem for graduate students. Okay. Might be difficult, but you can try. There are sort of another group of people studying this kind of things. A very classical result by Jacques Bay says properly convex divisible affine manifold is a cone. Properly convex divisible affine manifold is a cone. There's only cone if it is properly convex and divisible. Okay. Such a theorem exists long time ago. So far I try to focus on what geometric structures are and what are the examples and so on. Okay, so you saw hyperbolic geometry, projective geometry, and affine geometries. Okay, so now for the rest of the time, I want to give you some picture. What's the interrelation between these geometries? It's not deep observation, but I want to convey some ideas. What are the relations between these geometries? So let me start with, again, by hyperbolic geometry. So let me fix S is a closed surface with genus at least 2. Okay. Then by the uniformization theorem, this S has some hyperbolic metric, complete hyperbolic metric. Okay? Uniformization theorem tells you if you give a complex structure on the surface, then the universal cover is either biholomorphic to the sphere, okay, or the complex number C or unit disk. So if genus is greater than or equal to 2, then this complex structure is always biholomorphic to this unit disk. So it has a hyperbolic metric. Then, as I didn't mention it, but there's no reason that this geometric structure is unique, right? For example, I told you there is some hyperbolic structure, but by no means it is not unique. So you can think of all the hyperbolic structure on this surface is Teichmuller space. teichmüller space. So this is the space of marked hyperbolic geometric structures on this surface. And it turns out that this is homeomorphic to R to the 6G minus 6. Okay. So there are tons of different marked hyperbolic structures on surface. Okay? And then, usually mathematicians try to compactify the moduli space. So let me mention about the compactification of this moduli space. Then Thurston came up with compactification of the teichmüller space by projective laminations. So let me do this way. Let's say maybe this guy is included in the let's say R plus some S. So this is a set of functions from closed loop to a positive numbers. Okay. So what it means is that if you choose any curve on the surface, you can measure the length of this curve, which is a geodesic length of this thing. Okay. And here you have an image here. Okay. For each teichmüller metric, you can do that. You can associate a function like this. For each S is a set of free homotopy class of closed loops. Okay. Then you can compactify this teichmüller space inside this space. It turns out to be a projective measured laminations. Okay. So if you compactify this thing in this space, then the boundary of this teichmüller space is the set of projective measured lamination. Okay. Maybe it's better to draw some picture. So for example, if you have a hyperbolic metric here, to make it diverge inside the teichmüller space, for example, pick one closed geodesic here, like lambda, and you pinch it. So you pinch here. So at the limit, this guy is pinched. So it develops a cusp, actually two cusps. Okay. Then in Thurston compactification in this sense, this sequence of hyperbolic metrics, G sub I, obtained by pinching along this some simple closed geodesic, converges to a projective lamination, lambda. So projective lamination, lambda means here, this curve has a Dirac measure 1, and you projectivify it. Okay? So this sequence of metrics converge to some projective laminations here. Okay? But I want to see this picture in terms of convex projective structures. because hyperbolic structure is a substructure of the projective, strictly convex projective structures, tight cumular space is a subspace of the space of marked strictly convex projective structures. Okay. And now try to compactify such a strictly convex projective structures. Then you will see the compactification of the hyperbolic structure inside together with another piece of compactification. Okay? So I'm trying to give some ideas. How can you do this? So let's see. Maybe it's better to give some examples or definition. So let me think about what it means that a sequence of hyperbolic metrics converts to a projective laminations. Okay. So what does that mean? So tight cumular space, the space of marked hyperbolic structure is also can be written as is the set of discrete faithful representation from surface group into PSL2R up to conjugacy. So here conjugacy. If two representations are conjugate, they represent the same marked hyperbolic structure. Okay? Then if rho n converts to lambda, for example, in that picture. So rho n represent a representation or equivalently some marked hyperbolic structure. If it diverges to some projective lamination, what it means? It means geometrically this lambda is the direction along which the metric sort of blow the slowest. All the transversal directions blows stretch the fastest. Okay, that's the sort of geometric meaning of the convergence in Thurston compactification. So if it diverges like this, this means this. By scaling down the hyperbolic metric by some appropriate constant which goes to 0. Okay, suppose you have a constant coverage minus 1 hyperbolic metric. You scale down the metric by dividing by this thing. Then in this situation, what it happens is rho n converge to on isometric action on R3 dual to lambda. Do I confuse you, graduate students, or are you with me? Or so imagine you have a hyperbolic metric. You scale down the metric. Okay, you stand here. If you scale down the metric, for example, here and the distance between me and there was 2 meters. If you scale it down, it's become 1 meter and 0.5 meter. So standing from here, you can see far and far and far away. At the limit, all you see is sort of a limit things, right? The things nearby, which was a finite distance, sort of disappears in the limit. So this is an idea of Gromov asymptotic cone.